Hi, welcome back. Just before Christmas I made a video about a resistance standard box that Vishay had kindly made and sent to me for use with my videos and tutorials and within my own lab so that I can spot check my meters and things. The original ask that I had done to Vishay was just for a few sample resistors that I could use to build a small box that I could use for the same purposes, but they kindly offered to make one for me. Now, a few people have asked, well, how do they make it, what's inside, and things like that. So this is the box that they actually sent me, and as you can see, it's got one common connectors and seven basically decade sets from 1 ohm up to 1 meg ohm. Now, these are made with some very precise resistors, and we're going to go into the details of that in a moment. But basically, you know, the way that they've made this is it's going to pretty much last me forever. It's the resistors that they've selected to use inside this have almost zero temperature drift. They've been stabilized over time. They're hermetically sealed, so very little environmental changes will have any effect on the actual values of this. The details of which I'm going to go into in a moment when I bring up the actual PDF data sheets. So without further ado, let's go and have a look inside this. So right from the beginning, the one thing I want to point out on the outside of the box is that there's only one common for all of the resistor values that have been provided. But that's when you see inside, you'll see why that is and how that works quite well. I have values from 1 ohms, 10 ohms, 100, 1K, 10K, 100K, and 1 meg ohm. And all of these resistors on the non-common end are all 4-terminal connected. So effectively for each one, it's a Kelvin connection to improve the precision. Now you can see they've spray painted the box for me a nice blue and white Vishay foil resistor colors, but there's one connection up in this top corner that has been left unpainted. They probably drilled it out again a little bit afterwards just to remove the paint. And the screw is also, you know, I've already removed the screws, but the screws that they provided, they're all painted as well to make it look really, really pretty, except for the last one, right? And they've left this clear. And the reason for this is that if you're doing some precision measurements and you know, potentially have some noise and things like that, in order to help protect that, you can just put a ground lug on here and connect it to ground, which can reduce a bit of the interference. The case itself is a die-cast aluminum box, which also improves the shielding and everything else. And if you notice, all of these connectors, I don't know if you can see it on the camera, but they're all gold-plated connections as well, which again would improve the contact resistance and everything, and just go to reducing noise and any errors because of the connections even further. All right, so let's just open this up. I've already taken the screws out, as I said, so I'm just going to take that off, remove the back. As you can see, a nice clean die-cast box. And let's turn this over and have a look at what's on there. So the first thing to notice once we have a look inside here is that there are 3 kinds of resistors. We have this multi-chip 1 meg ohm resistor, and if I look on the side here, it's actually marked as 1 meg 0000, and it's a 0.01% tolerance resistor. Richard from Vishay told me that this is actually one that he's had for quite a few years, and it's basically as solid as bedrock now because it's aged, it's stabilized, and it's probably never going to shift in its values anymore, either because of humidity or temperature or anything like that, as long as you don't abuse it and you keep it within its you know, its tolerances. So every one of these are rated at least 300 milliwatts, but Richard's recommendation and Vishay's recommendation is if you keep it to less than 1/4 milliwatt for your power dissipation in these things, you're going to have no issues with drift or anything like that. The other thing to notice is that these higher value ones, so we've got the 1 meg, 100K, 10K, 1K, 100 ohms, they're all VHP 101 type of precision resistors from Vishay. The last two here, which is the 10 ohms and the 1 ohm, these are VHP 202 resistors. Now, the one thing you'll also notice, I don't know if you can see it just behind here, is there is a second resistor on here, which is another Vishay Precision film resistor. This value is 40K at a 0.01% tolerance. The reason that's there is probably because this 10 ohm resistor may have been slightly out of tolerance, and what Richard did was put a 40K in parallel with it to pull it in. So let's have a quick look at the specifications to see what these resistors are all about. So like I said, the bulk of the resistors in this standards box are the VHP 1100 series, and here's the data sheet I just printed out from Vishay for them. As you can see here, the first thing is, of course, their foil technology, their ultra precision, and their zero temperature coefficient resistors. That means that with temperature, to all intents and purposes, they do not drift at all as temperature changes. Now, because of this, they had to recategorize the way that they presented the temperature coefficients of these resistors, because they changed so little that the values that would be getting presented would be pretty meaningless. So if you look at this, they're actually featuring the absolute resistance change. And so for the VHP 100s, that's 60 parts per million, but that's total change. So it's 60 parts from minus 55 to plus 125 degrees centigrade. Equivalent other resistors might change as much as 900 parts per million. And I'll show you a little bit with that in a moment. The VHP 101s, which are the ones that Richard kindly put into my box, are the VHP 101s, and these are actually less than 10 parts per million change between the lab range of about plus 15 degrees C to plus 45 degrees C. So these are exceptionally stable resistors, where if you have them in a standard home lab or even industrial scenario, you're never going to be outside of this normal working range of plus 15 to plus 45. And even if you did, and you go to the extended military range, you're still going to be well within 60 parts per million total change over the range of minus 55 to plus 125. And of course, if you're staying within a relatively human comfortable environment, then they're going to be changing less than 10 parts over this plus 15 to plus 45 degrees C temperature range. So you really don't have to worry about them changing at all. You know, if you're in your basement like I am and it's about 22 degrees, or if you're in somewhere where it's a little warmer, even as much as 30 degrees, 35 degrees, or even cooler, it's going to make no difference at all. There is no humidity effect. As you notice when I showed you the picture of the box, all of these resistors are contained within metal cans that are hermetically sealed, so you can't get any moisture in there. The thermal EMF is the lowest in the industry. They've got excellent stability, and there is no inductive performance effects of these as well. All right, so if I just scroll down a bit, I'm not going to go through everything on these specification sheets, but for comparison, here is all right, a typical 5 parts per million per degree C resistor would be contained within a window of 900 parts per million. Now, remember before I mentioned that these resistors, the ones that I have on this box, are 10 parts per million total. So if we look at the military range of minus 55 to plus 125, where the VHP 100s have a 60 parts per million change, 5 parts per million per degree C from minus 55 to plus 125 is 5 parts per million times 180 degrees C, which is the range. That's 900 parts change. Whereas these resistors, worst case with full industrial range, have 60 parts, and within the lab they're only 10. So you can see it's a magnitude improvement. Actually, no, 2 magnitudes, so it's 100 times better almost than most typical resistors. The other nice thing about these resistors too is they have significantly long leads, which allows you to do 4-wire connections. So these resistors have exceptional performance and tolerances, and you can get them anything from 1% tolerance all the way down to 0.005% tolerance. And in a lot of the Vishay resistors, you can actually specify what value you want as well, and they will actually make it to your value in a lot of cases with no additional cost to the buyer for that. And you know, for the VP 101s, which is the one we're looking at right now, they range from 100 ohms up to 150 kilo ohms in value, and you can have anything from, as I said, 0.005 to 1% tolerance. They're specified as 300 milliwatt at 70 degrees centigrade rating, but you know, usually you would keep it below about 1/4 of a watt if you want to improve the life of them. Shelf life stability, if you look at this, is 305%, so 5 parts per million, which is exceptional. Thermal EMFs A lot of resistors I've looked at have been several microvolts per degree C. These are down at 0.05 microvolts per degree C, and that's due to temperature differentials between the leads. Within self-heating, so when you're actually applying any any current through a resistor, it's going to generate a certain amount of heat within itself. It can't be helped. It's just the nature of what they are. These will drift about 2 microvolts with a 100 milliwatt load going through them at worst case, so between 0 and 200 microvolts. Inductance is a high frequency operation. It will support a rise time of 1 nanosecond for the 1 kilo ohm value, and its inductance is 0.1 microhenries or 1 picofarad for the capacitance, which is really, really good. And that's the worst case values. The typical values are 0.08 microhenries and a half a picofarad, and that's for a lot of high frequency applications or very sensitive, maybe an ADC input stage and things like that, where you're looking at high frequencies. It's very important that you have low capacitance, low inductive features on your resistor so that they have little effect on your overall design. This is the general spec sheet for the VHP series of resistors, and the VHP 202s that I have come in this hermetically sealed can, like crystal kind of can format as well. The VP202s though, the ones we're looking at now, these basically range from 5 ohms, the ones I've got, from 5 ohms to 50 ohms. Now I actually have one that's 1 ohm and 10 ohms in here as well. So they must be a special find that Richie got for me. The temperature range for these, 2 parts per million, typical from -55 to plus 125 degrees centigrade. 0.001% tolerance capability. Load life stability 0.005%. They're designed for metrology, laboratory instrumentation, and industrial use. They're using the Vishay bulk metal foil technology for these. They're one of the new technologies from Vishay, and they're extremely stable and good quality resistors for this purpose, for like a standards lab or something. If I just move onto the next sheet where we can actually look, this is an example of effectively the foil print or part of it that they have. And one of the things that they do when they're actually trimming these, if you've specified that you want a specific value, is they actually nibble away at these little bridges to basically increase the resistance up to the exact value that you specify. So they'll make them to a certain value below what, within certain ranges that people will want, and then when you specify what you want precisely when you're ordering, they will actually trim these down to the exact value before they then hermetically seal them into the cases. The ones I had, as I said, were the VHP 202s, which the standard range that they go from is 5 ohms up to 100K. The specific features of the VHP 202 that Vishay included in the box that they built for me here are they have a max working voltage of 300 volts. Now obviously depending on the value you can't put 300 volts across all of them. They have a power rating of 300 milliwatts or 200 milliwatts if you're in the 100K to the 150K range. Below 100K they're 300 milliwatts. And they're also oil filled, which is really not often you see that with resistors, but because these things are designed for precision lab work and things like that, of course they need to improve the ability to be hermetically sealed and not be, to reduce temperature effects and things like that. So the oil inside the can will help to dissipate heat straight to the outside and get rid of it. It'll also prevent any humidity and things that might have got in there from, having no effect. So basically they just get rid of all of the air out of the container and they've filled it with oil. So going back to the actual box that Vishay made for me, so like I said before, the resistors at the high end here, the 100K, 10K, 1K and 100 ohms are all the VHP 101s. So at the top end of the range we've got the 1 mega ohm resistor. This is a multi-chip hermetically sealed but potted package, which is, as I said before, 0.01%, but Vishay has kindly measured them to a much better tolerance than that for me, which I'll show you in a moment. The 100K, 10K, 1K and 100 ohms are all the VHP 101s, and then you've got the VHP 202 and for the 10 ohms and the 1 ohm. Now the one thing you note here is that there is a very, very thick wire, but it's copper, tin-plated copper or nickel-plated copper wire, and it runs from just a support bracket up in the top left corner along all one side of the resistors, and then up to a pair of banana plug sockets, where this represents the beginning of the two terminals. So if you come in, the black connector being your current side of the measurement, then your measurement current would come into here. You've eliminated the contact resistance because your voltage measurement would be measured from the red connector. So any resistance that might have been incurred, even for this 1 ohm resistor, has been eliminated because you're basically ignoring the current in, which is on this black connector, and the current out, which will be at the other end through the resistor and on this black connector. So your voltage measurements in this case would always be done between the two red internal connectors. And so because of that, with Kelvin connections and everything else, and because your input impedance of your multimeter is typically 10 megohms or more, there is no notable voltage drop at all from measuring the resistance on here. For the higher values, of course, as you go higher and higher, the contact resistance becomes less and less important. So what Vishay have done for this box for me is that they've only put one common, and then they've ran all the resistors onto that. Now you've already eliminated the contact resistance because of this very first one. So all of these other ones, really, if you look at how thick this wire is and everything else, there's going to be no negligible resistance drop that you're ever going to pick up for these values. And of course, this, Vishay has done the sensible thing in that the low value resistors are the ones that are closest to the original Kelvin connections, and as you go higher up in value, they're further away. And of course, this final one being 1 megohm, even though there's probably 8 inches of tin plated or nickel plated copper wire here, it's very, very thick, and overall, with 1 megohm here and maybe 0.01 ohm or less on this piece of wire, you're never going to notice it anywhere close to within the tolerances of what the resistor is. Each of the other sides of all of these resistors, of course, have maintained their proper Kelvin connections. So you've got the current side and your sense side for every one of them, and the wires coming out of the package have been wrapped around the first terminal. I don't know if you can see that very well here, but what Richard did when he made these is he took the resistors, wrapped the wire around the terminal to improve the contact resistance, and then brought it down and wrapped it around the second terminal before he soldered these into place. And if you look up here on the right hand side here, you can see it quite clearly. Even if I zoom in there, if I can, you can see that Richard's actually taken some heavier duty wire, not as heavy as the main bus wire, and has actually wrapped it around the common connecting wire here, round the terminal and back on the other side, which again is improving the connection quality significantly compared to just if you had it contacted, because obviously the resistance of the solder is a little bit higher typically than what you would have with the actual physical contact of the cable. So this has improved the surface area of the contact massively compared to what you would normally have. And the same with the the voltage sense size is the same thing. So every one of these has been wrapped to improve the connection quality, right? And that's pretty much it. The box is die-cast aluminum, your standard kind of project boxes you can pick up from most hardware suppliers and electronic suppliers. The wires that are the thinner wires are all the ones that are built into part of the resistor here, and the really thick wire is heavy gauge cable. And then all of these BNC connections, you can get these readily available from almost any electronics supplier, and that pretty much will complete how this thing is put together. Now Vishay have been very, very nice to me and provided these VHP 101s and 102 resistors for the standard I've got here, but you can actually buy some very precise resistors from Element 14 that have 0.05% or better tolerance. They just may not be as thermally stable as these particular ones. So having a resistor that has, say, 10 parts per million per degree C or 5 parts per million per degree C tolerance, if you're going to be keeping it in your home lab or office lab, and the temperature is typically going to be the typical office temperature, which is say between 18 and 22 to 24 degrees centigrade, then the actual drift that you're actually that you're going to go see with that kind of resistor is still going to be absolutely minimal. So you can save yourself some money by buying lower TCO resistors, but don't go too crazy, because you want to be able to know that at your normal environment it's going to be keeping its value correct. So in summary, as far as building your own home resistance standard box, you don't have to have as many values as this. You could reduce it down to maybe just 4 values or something, because as I said, it is a spot check, and most multimeters only have maybe 4 actual values of resistance range. So you just have to pick one that's representative of that range. The second thing is these have very, very high, almost negligible temperature coefficients for all of these resistors. They're hermetically sealed and in some case oil filled. They've been aged and everything else. So these are ultra stable over temperature and time. For a lot of home use, you don't have to go to that extent. You could put effectively some regular axial resistors in here. Even Vishay have a number of more cost-effective ones that are still very, very high tolerance, but perhaps not quite as expensive, and they probably don't have as high a temperature coefficient. But if you consider the fact that you're going to leave them in your lab/office environment with a fairly stable temperature change, maybe only 5 degrees total, then if you've got a 5 ppm TCO resistors that you've used, then that's only going to give you 25 parts out of a million, which means it's still going to be well within the range of tolerance for most handheld digital multimeters and even a lot of the bench ones, unless you've gone to the more expensive 6.5 digit or 8 digit bench multimeters. And if you're going to be doing a spot check on resistance for those, you could have a few values that are lower temperature coefficient and maybe just opt to have a couple of the high temperature coefficient values. It's all up to what your budget is and what you're trying to achieve with your resistance standard. But hopefully this has given you a good insight as to how the professionals, namely Vishay in this case, build a resistance standard, and they were very, very kind enough to build this one for me. I don't think I would have realized to do a lot of the features of how they built this, like wrapping the wires around a lot and things, and having the common bus for the Kelvin connection and stuff like that. So it's very enlightening and informative to see how they've done it themselves. Anyway, that's that. So let's just go now to the looking at what these values actually are and how they fare against my multimeter. So this is the calibration sheet. I mean, obviously they were doing this for me as a favor for just before Christmas, so it's not what you would call an official calibration sheet. But Richard from Vishay was kind enough that once he built this for me, he measured every single one of them to a very high level of tolerance, and because these are very, very stable resistors, they're unlikely to change over time. So you can see the 1 ohm resistor here is 4942 ohms, 0.4942 ohms. The 10 ohm resistor, 1, 2, 3, 4, 5 zeros, 4. All right, so these are going well within 1%, 0.1, 0.01, 0.001. So this is like 0.0004% off from its value. Now that's 1, 2, 3, 4, 5. You'd have to have a 6 or 7 digit multimeter to be, or bench meter to be able to detect that difference. And as you can see, every one of these is very, very accurate. There's the 10K, the 100K is ridiculously accurate here, and the same with the 1 meg, 100.0001K. You really couldn't ask for much better than that. Like I say, a lot of these resistors that are in here, their actual base tolerance might be only 0.01 or 0.1% for some of them, but they are ultra stable, and it's just what they're made to. And then because Richard has selected these individually for me, when he built the box, he was able to measure them and tell me precisely what the value is. Now, even if you bought 0.1% resistors or something like that, if you were able to have them measured accurately, then they're not going to drift over time anyway, as long as you look after them properly. So even if they were a little bit out, it's about what the value is, not about the absolute accuracy for testing your multimeters. So anyway, that's the cal sheet that I have there so that I can reference it when I'm looking at my multimeter. So let's just go get one of my Agilent U1272A, hook it up and see how accurate it is compared to the resistance standard. Alright, so what I've done here is I've just hooked up my multimeter, the U1272A Agilent, and I've got some very short, heavy-duty cables that I'd made up for basically jumpering my power supply to parallel the outputs. So the reason I've used these ones is because they obviously have a very low resistance compared to a lot of the typical meter wires. So these would probably handle about 20 or 30 amps without getting too warm. But my main thing here is that they're very short and they're heavy gauge, so it just minimizes the external resistance. Anyway, right now they're hooked into the 1 ohm resistor. Now obviously the U1272A does not have 4-terminal capability, but you can still get a good idea of how accurate your meter is. So there's my 1 ohm range. Now remember, the value of the 1 ohm resistor here is 0.999942. So I'm reading just a very tiny bit high here, but I haven't actually zeroed out the meter or anything. All right, so it's 0.999, and that's the resistance value. And I haven't, like I said, I haven't zeroed anything out. If I take the connections and just connect them together to try and eliminate, all right, so I've got no offset anyway. So this is reading as accurate as it's going to be for the 1 ohm range. So as I say, the resistor is 0.9999. I'm reading 1.000. For a meter, that's pretty much spot on. You couldn't ask for better than that. Now if I start moving up the ranges, we'll see how we fare. All right, so that's the 1 ohm. Now I'm going to connect it to the 10 ohm resistor. All right, so 10.0009. The 10 ohm resistor on here is 10.00004. So as far as this is concerned, it's 10 and 4 zeros after the decimal place. So I'm a little bit out from what I'm reading compared to the standard, but I am well within the tolerance of the Agilent multimeter. All right, so this is still reading 10%, 1%, 0.1%, 0.08% tolerance. And I know that if I look at the spec sheet for the resistance range of these multimeters, they're not that accurate, so that's pretty good. Let's go up to the 100 ohms and see what we have there. All right, so that's 99.99. That's pretty good. Now, I'm just shifting this between the two different ones. It's drifting just a tiny bit as my multimeter is warming up. I just want to make sure that I didn't mess up some of the other values because of where I connected it to. So that's 10.00056, 10.0002. So it is making a difference every time I drop this in here. But it may be because I'm not doing 4-terminal, the difference in the last digit of reading could be simply because of the contact resistance when I'm pushing it in and out. All right, so I mean, you can see that's drifting down very, very closely to the 10 ohms. Now my multimeter hasn't been on very long, so it may have a little bit of drift just as it warms up a little bit, but insignificant. So back to the 100 ohms, 99.98. That's pretty darn good. We'll flip up to the 1K. All right, 99.998. Now, obviously, as I said, my resistors in the standards box, they're very accurate. So, the fact that my multimeter is maintaining a similar accuracy is quite amazing. Let's go down to the 10K. So 9.998. That's pretty good. 0.02%. 100K. 99.98, 99.97. So that should be 100. So it's 1%, 1%, 0.1%, 0.02, 0.03% accurate, which is pretty good. Now the last one, this is the last value I've got. I have to move the multimeter a little bit to make the connection. That's the 1 megohm range right there, and you can see 1.0001 megohm. So there's this quick spot check of my multimeter, and I think I would be happy to say that any resistor I read up to, say, a meg or 2 megs, right down from about 1 ohm, I could rely on the actual meter reading being pretty much spot on, providing I have a good contact resistance to the resistor that I'm measuring. So I think that's pretty much concludes resistance standards, a little tear down and run through. I'm certainly very, very happy with what Vishay has provided to me. And if you do decide to build your own, then I think you'll find that, as you can see from the inside of this one when we looked at it, it's not terribly complicated. You just got to be neat with your wiring. Make sure you get a lot of contact like surface contact by twisting your wires around the posts and things to improve the contact resistance. And you know, you can quite happily have your common bus, which remember was what we have with this, running from the common and then to the top end of all your resistors, and then keep the bottom end separate. Now the only downside of that, which is not really a downside as far as I'm concerned for my use, is that you can't have something connected to the 10 ohms and something connected to the 10K at the same time, because obviously they're all sharing a common end. So you'd end up effectively putting them, the resistors in parallel, unless you have two completely separate circuits, but you could still get effects from the current and things. But anyway, that's it. So I will sign off there at the end of this video tutorial, and a quick teardown of the Vishay foil resistor standard box that I was provided with. So hope you like it, and we'll be back soon with some more examples of Vishay's resistors that I have here that I'm going to be using for my bench power supply and DC load circuits that will be getting put on air soon.